Uh, no, you can keep. Welcome, everybody, to this new session of the Chilean Probability Seminar. So today we have the pleasure to have with us Aleksandra, whose last name I will not try to pronounce. She comes from EPFL in Lausanne, and she's visiting for 3 months here. So many of you have already seen her. She's doing her PhD in Lausanne, and profit that she's going to be around at least almost 2 months more around. She's leaving the 12th of September because she didn't want to leave the 11th. So she will talk to us about these recent results that she has with Yuhanaru, where they see appearing the Gaussian free field from the spin O model.
Okay, thank you very much for the nice introduction and the opportunity to talk here. So yeah, as already mentioned, today I will talk about statistical mechanics models. So one of them is called spherical and the other one spin O model. And basically we will study these two models through, various versions of Gaussian free fields. Okay, so the main focus of today's presentation will be the spherical model. But I will also mention the results that we have on the spin O. So I will start by introducing the two models and explain their connection, because actually from the physics point of view, these two models are also closely related. And also I will give a reminder on the Gaussian free fields that we will use. And of course, then I will move on to our results. I will try to motivate and give an intuition behind them, and then also state them and try to explain at least the strategy of the proofs. Okay, so let's start with the spherical model. So this model was introduced more than 70 years ago by Berlin and Kac. Yes, so what is this model? It was introduced as a simplification in some sense to Ising model. It's not quite physical model in the sense that it doesn't have like Hamiltonian in a proper sense of what it is. But this model is still quite nice because, in physics, if one understands something which is called free energy, then one understands the model in some sense. And in this model, this quantity can be computed explicitly. So, and also this model is not trivial. In dimension 3 and higher, it exhibits a phase transition, while in dimension 2, actually, it doesn't. So how is it defined? So it has a form of, is there a pointer here?
Yes, but it doesn't show.
Okay. So, it has basically, in some sense, a Gaussian form. So what we are taking is basically the standard interaction. So what we are looking here at is we have a torus, and then at each vertex of the torus, we have a random variable leading. And then we are basically, in this model, we condition then the norm of the total vector, which is indexed by the torus, has the size of the square root of the volume. So basically, this is represented in this formula. So we have the interactions similar to the Ising model. However, now we basically live on the MD-1 dimensional sphere, and we choose the normalization, which corresponds to the volume. Yes, and the two main methods that were used to study this model are steepest descent one. So basically, this is the one that was used by Berlin and Kac, and also there is actually a note by 2 Russian mathematicians. So it's like a paper in some Soviet journal, where they basically give a bunch of theorems without any proof. They say that with this method one can obtain them, and actually some subset of these theorems we prove in a different probabilistic way in here. And then there is a second approach, which is in somewhere it's called mean spherical approach, somewhere it's called a Lagrange canonical approach. So what happens in there? So actually this kind of conditioning where we precisely work with this equality is quite complicated from the computational point of view. So in physics, people said, well, but it's too complicated, all these computations, let's simplify the life. So what they are doing is basically they're adding a math term here. So they subtract here minus some s squared sum over theta x squares. And then basically they are looking not anymore at this condition, but under this new tilted measure on the event where on the average, under the new tilted measure, we have this equality. However, there is a problem with this approach. So it works in the high temperature regime. So when everything is disordered enough. However, one observed quite quickly is that, well, there are some discrepancies in the low temperature regime. So when temperature is very low. However, so this method was proposed by Lewis and Bonner in 52, but then one of the authors with another physicist in 65 kind of fixed the problem. So basically they said that actually if one also adds an external magnetic field, then takes the thermodynamic limit. By thermodynamic limit, I mean this n goes to infinity, and afterwards the external magnetic field to 0, then basically one gets back to the results of Berlin and Kac, and so basically the discrepancies disappear. And then after this kind of fix was found, this method or its variations was also further used by many other authors to study this model and modifications of it. Okay, and maybe let me also mention one more result, which is actually a recent result. So this model also can be complexified in some sense, in the sense that, so here theta one considered to live on in C instead of R, and one modifies the measure slightly, and basically in the so the author is Lukainen. So in 2020, the paper is from 2020. So there's looking at the model in what we call here low temperature regime, but basically, so it's the temperature where this kind of drift term appears, which in physics represents something which is called Einstein-Bose condensation. So in this context, the author studies a complexified version of this. And basically, if one looks at his result using one small technical observation, one can conclude also the low temperature regime of other results. Okay, now to the spin O model. The model is very similar. We have now a slightly different setting. So we still work on torus, but now on each side, so before kind of we had a vector which was indexed by torus. Now we have a collection of n capital dimensional vectors which are indexed by the torus. And now the condition lies not on the whole torus, but on each vertex. We assume that basically the vector that lives here lives on the n-1 dimensional sphere of according radius. And the potential is the same. So why these two models? Okay, so actually from the physics, one knows that these two models, when n capital goes to infinity and the thermodynamic limit when the volume goes to infinity, they well, coincide in some sense. And by coincide, we mean that they agree in the free energies. So basically, this is exactly the statement. So this quantity is what is called free energy, minus this quantity is what's called free energy. And this quantity is like free energy per speed. So here we kind of normalize by the number, by the dimension of the speed. Okay, and then Katz and Thompson in 71 proved for non-critical temperatures that this equality is true. And for the critical case, one could well, read it out of these two papers, Sherbina 89 and Goffin Poulet 93. Okay.
Can you, maybe I got a bit lost.
Yes.
In the first one, you choose.
Yeah. let's look at the picture. So here I have the torus.
And
At each torus, you put one-dimensional thing, and then you condition on the sum over all the points. So basically, you now consider it as a lambda dimensional vector. While here, you have n times lambda dimensional vectors, but you put the conditioning just on the vertex.
each of those.
Yes, on each vertex. So they are kind of not as correlated in the sense as in the other model. Okay, so now let me just give a very quick reminder on the Gaussian free fields that we will use. So we will use massive Gaussian free field. So what is it? So basically, okay, the way I wrote here, the density, so it's basically a multivariate normal variable which has a specific correlation function. And when one rewrites this correlation, inverse of the correlation functions in a nice way, one gets such a density. Basically, if one opens up now the bracket, we will see that the covariance is actually nothing else is, well, it's an inverse of, so at least if U is empty. So here I assume that I give the general definition where we maybe put some zero values on, assume that it's has zero values on some set. But okay, let's just ignore this part. Suppose we are on torus, and yes, we have this. So then the Green's function is nothing else, it's just the inverse of minus Laplacian plus m squared in this setting. And in terms of random walks, where alpha is chosen to be m squared divided by 2d plus m squared, and xn is just a simple random walk on lambda n, it's given well, by this formula. So basically, it's the sum of visits of starting from x of y before you either like jump to a symmetry state or hit the u if this u is not empty. Okay. So here is the simulation by Aleksandra. Actually fits a very nice color in the color scheme of the presentation. So yes, okay. The zero, now I will also mention a zero average GFF on torus. The problem when we work on torus is that so if m, the mass in that GFF is 0, we can't really consider u to be empty because the Laplacian on torus is not invertible. However, there is a different natural parameterization, well, fixture of this problem. So basically, instead of assuming that we are at some point 0, we can assume that the average is 0. And, well, the result is what is called zero average GFF. So basically, the density is the same. So now mass is 0. However, we now basically assume that the average of the field is 0. And there is an associated Green's function, which is the covariance matrix of this field, which in terms of the random walks, so it's not really an inverse of Laplacian anymore, because basically it's kind of, it has to have average 0. So the sum, so if x is fixed and we take the sum over y, this function will give 0. Yes, so in terms of continuous time random walk, it can be really represented in this way. Okay, so now why at all did I bother to present the GFFs and how are they related to our model? So actually, the relation is quite simple if one recalls what was the. So for the spherical, our density with respect to uniform measure was basically sum over beta theta x, theta y. Well, but I can just do something. Note that this is still proportional to that because we assume that this is just equal to lambda. So basically it's fixed. So, and this can now be rewritten in terms of theta, well, minus beta half still stays there. And here we get minus theta plus, oh, sorry, I need to add 2d plus m squared. Well, 2d is to get the Laplacian and m squared to get this mass. Yes, so basically, you can rewrite the exponential in this way. And well, as we will see, so the only thing we were conditioning here is on the norm. And this explains this relation. So namely that the law of the spherical model is nothing else as the law of any massive. So for any positive mass, conditioned on the norm to be beta to nd. And for the low temperature regime, we will use a bit different relation, but I will explain how to see this field appearing from here. So the other relation that we can observe and that we show is true is that the law of the spherical model can alternatively be written as so if I want to put mass 0 there, it doesn't quite naturally work because Laplacian is not invertible, but actually an easy fix would be to add a Lebesgue constant and then condition on the sum of the two things to be beta and d. And the thing is that, so why this form c times the 1 lambda here is just the vector of ones for each point you put a 1. And why is this? It's because like the eigenvalues of this zero average Green's function are actually nothing else as the inverses of positive eigenvalues of minus Laplacian and 0 eigenvalue extra. So instead of infinity, we substitute the inverse of 0 eigenvalue from Laplacian, we substitute 0. So basically, if one thinks of rotating the whole story, one kind of sees that here we take something proportional to lambda, and this c would actually make everything work. And a similar story we have for the spin O model, except for now we are taking the vector value GFF, and because the conditioning in the spin O model was at each vertex, so basically that's what we are doing here.
So just the independent Lebesgue constant means that somehow you don't have a probability law, but you are looking at one fiber. No? I see.
Well, so kind of. So when I say that, I mean that the law of gamma. So okay, law is. So this one is just 0 average GFF times Lebesgue measure. And the thing is that so a priori it's not a finite measure, but when we do this conditioning, it basically becomes a probability measure. So for example, if one restricts this one to a ball of size square root of 2 square root of nd, then it would be a probability measure. So you rescale and then you work as if it would be a probability measure. But yeah, so alternatively, one can think of it, one starts again with here, and then one basically gets a mass that is like very large. And then through conditioning, one gets that it has to be constant. I will explain why this. So I will start with this really easy observation and show how it makes sense to arrive to this. Okay, let's look at the spherical model and use this observation exactly. That the law of the spherical model is just the massive GFF condition on its norm to be some specific quantity. Okay, so let's go back to that physics idea that I mentioned, that, okay, maybe if an expectation, everything looks nice, then it would be sufficient, which turns out not to be exactly the case everywhere. But okay, so how do we choose the mass? So what would be the natural choice? So that the expectation under this tilted measure is exactly beta and d. So this is basically the idea of Lewis and Bonnier. Okay, so this results into just a unique choice of mn squared such that g lambda and mn squared is just beta on the diagonal. Okay, and actually, if beta is less than beta critical, where beta critical is actually just the Green's function on ZD on the diagonal. So recall that this Green's function is infinite in dimension 2. In particular, there is no phase transition in dimension 2. And in dimension 3 and higher, there is a specific value for that. Okay, if beta is greater than beta critical, and this is kind of the motivation why it all look at zero average GFF instead. So basically, if one rewrites, for example, this equation, one would see that to satisfy this equality, one has to choose mn squared such that it's proportional to beta minus beta critical. And then basically, in this scenario, if one just rewrites these functions properly, one can see that this massive Green's function can be rewritten in terms of zero average Green's function. So these functions for fixed x and y, if m is fixed, they both kind of converge to, well, okay, if m converges to 0, so yes, so basically if m is positive, this term kind of is irrelevant. However, if we choose it such that it's is saying macroscopic, then we see that because we are on torus, kind of this massive Green's function doesn't converge to the massive Green's function on ZD anymore. Rather, it converges to, or like to just Green's function on ZD. It converges and we get some extra drift, which is beta minus beta critical. So this explains that approximately we can write this massive GFF on torus as the zero average GFF on torus plus, okay, beta minus beta critical comes from this expression times some normal one, because these are covariances, well, and these are independent. So, well, we kind of, if we sum independent normals, then the sum of their covariances would be exactly the covariance of this guy. So a priori, we get this guy, and one could try to look at it. But yes, and so this is also explaining like where the argument of Lewis and Warrior kind of shutters. Because if beta is greater than beta critical, contrary to naive expectation that this would be sufficient to eliminate the conditioning, it's not. So if we start working with this object instead, we still we basically end up with this conditioning. And as I mentioned, the 1 over lambda is basically orthogonal to all, to basically any non-zero eigenvalue corresponding to eigenvector corresponding to non-zero eigenvalue of the zero average Green's function. So basically, this, when one opens up the brackets, is basically just gamma squared plus beta minus beta critical z squared times nd. So we have gamma squared plus beta minus beta critical nd. It has to be equal to beta nd. Well, if we now divide everything by nd, z squared, we see, okay, it's quite obvious that this has to converge almost surely and extremely quickly to the expectation. So, and the expectation of this is just beta critical. So it basically forces d squared to become constant. And this is what, yes, and by symmetry, we have to consider a Rademacher random variable. So this is kind of the motivation. So instead of making all these steps precise, we just kind of directly start with working instead of gamma and some normal, we work directly with gamma plus this Lebesgue constant. And then show that the Lebesgue constant becomes Rademacher random variable under conditioning. Okay, maybe let me skip spin O. Basically, idea is the same, except for, let me first make a small remark that in our result, we first consider just n capital going to infinity. So the spin dimension going to infinity, and then the thermodynamic limit, because in this way, basically what happens is that when we first take n capital to infinity, we are in some sense in the low temperature. We basically can argue as in the low temperature regime of the spherical model, and we get a Gaussian. So we show that we get a Gaussian, and once we know that we are a Gaussian, when we take a subsequent limit, we only need to understand what the covariance is doing. So, and then basically one can show that this holds. And the other thing. Okay. So our result is the following. So as you probably have already understood from the intuition, so in the spherical model, when we take n to infinity, we get in the limit below the critical temperature, which is the Green's function on ZD at 0, 0 on the diagonal, a massive GFF with m squared chosen, with the mass chosen in such a way that we satisfy this equation, and above the critical, above the inverse critical temperature, we get, so this is low temperature regime. We get the GFF plus this, well, constant in norm drift, but of course by symmetry it has to be a random available. And for the spin n, when we first take n capital to infinity, spin dimension, and then the volume of the torus, we get the vectorial GFF with m squared chosen the same way, and above the vectorial GFF plus this time normal, constant in space, but normal in the spin dimension variable. And the most interesting one, and actually the one which required the most work, is the critical temperature, and that one also appears to be like completely new in the literature. So basically here, well, we expect, of course, that we just get the GFF, but in dimension 3, and yeah, in dimension 3, it was actually a pain to show it. Okay, so
so just understand is that I mean, the Rademacher is just one Rademacher, the same one for everyone.
Yes, so basically on the whole ZD, you put one random variable. So at each point you put the same random variable, but yes, it's symmetric. So you either plus or minus. Okay, so basically how does the proof works for the...
So just understand, so if you look at the 2-point correlation function of the sign, that's 0 in, I mean, it's going to 0, exponentially to 0 in one case, and it's not going to 0.
Yes, exactly.
It's like some missing type of phase transition.
So it is a phase transition, and basically, yes, there is an exponential decay, then polynomial at the critical, and well, some constant in the non-critical, below the critical temperature in terms of Rayleigh temperature. Okay, so well, for the high temperature regime, basically the proof is quite simple. So, okay, we proceeded through density. So actually we showed result not just in law, but for the density functions. So yeah. So the idea is, okay, we know that the spherical model has the law of this conditional GFF. We rewrite it nicely using some the main Markov property of GFF. And basically we get the ratio where we compare the, so this is now has the law of the GFF with the zero boundary condition on some fixed box U plus some massive harmonic extension. And this one is just GFF on torus, massive GFF on torus. And basically, when m stays away from 0 in the limit, one can show that this ratio converges to 1. And the idea behind it is, well, quite simple. So we just prove some sort of CLT type of result, but just for the density function. And actually, recently, I found that one can also use some Malavian calculus type of result where to also imply this. So basically we show that if mn squared chosen in such a way, so basically it says that mn squared would converge to a positive number, then this ratio is just vanishing, and this density clearly converges to what we want, to the GFF, to the massive GFF. Okay, and so for the CLT type of result, the two main ingredients were, well, that the eigenvalues of this Green's function are uniformly bounded, and that the probability density function of the square of Gaussian is basically it has a higher moment than first moment. Okay, so my favorite one, so the low temperature regime. So why is my favorite? Because it's kind of quite intuitive. Okay, so instead of looking at the sum directly, what we will be looking at is at the conditional, at the joint law of the zero average GFF and this Lebesgue constant conditions that their sum, that their norm satisfies the required equality. And then what we will show is that it converges to the project measure of the GFF and the correct Rademacher random variable, and this basically would complete the proof. Okay, and it's a favorite one because basically once one finds a nice way to rewrite things, it's kind of clear that things will work out. Okay, so basically if we look at the joint law and using densities rewrite things nicely, so here basically this gamma is also done. So the nice feature of the normal distribution is that if we condition on well, some part of its vector values to take some specific number, the conditional law is still Gaussian with just some shift here and a slightly changed covariance matrix. But all this is very explicit. Yes, so then we end up with a ratio again, a ratio that we want to show that converges to something. And this ratio is just, it looks quite nice because, okay, we here see the gamma squared divided by nd, and as well as one can expect that by some sort of law of large numbers, this would converge just to the expectation, which would be beta critical. And here we take beta critical. So actually, like if this function would have been bounded, we could already conclude. Of course, there is a tiny problem that this function has like a singularity at when gamma squared nd is beta. So we just need like a few technical results, well, technical fixtures to show that actually this singularity doesn't matter. Okay, so what are we doing? Of course, the first step is the most obvious one. We show that these both things converge to almost surely to beta critical. And then we also conclude that actually this gamma squared nd is concentrated around its expectation exponent. So basically, sufficiently far, like on some epsilon from the expectation, we're actually exponentially decaying. So actually, we get these first 2 points by standard measure, concentration of measure results. And then the last part is now, because this is so highly concentrated around beta. So when here, this guy, so the only problem is basically, as I mentioned, is close to beta. So, but this beta minus epsilon beta interval, we can split further in like this very small one, like infinitesimally small one, where we will just integrate 1 over square root of x, which is an integrable function. And because we have exponential decay there, it would beat the 1 over nd, which would appear. And for the other part, we just use exponential decay. Okay, so for the tiny infinitesimal piece, we only need the boundedness of the density function, then we are good. And this one is easy because basically one just uses some Young convolution topology and all works well. Yes, so once we concluded this, then basically second, well, the 3 steps give you that it's singularity nothing happens, and then on the rest of the interval one can just use the DCT and conclude. Okay, now we come to the critical case. This is the one which poses the most problems. There was one technical result which I'll comment on later. Okay, so this guy, as we already discussed last time, converges to the expectation. However, the expectation of this thing is approximately beta critical. So in the limit, it would be beta critical. So kind of divide, so we'll get 0 here and 0 here. So things are not looking nice anymore. So because, I don't know, we're dividing 0 by 0, then we need to know how quickly things die out, which is not very nice to treat. So instead, what we tried to obtain, and our inspiration was actually the high temperature regime, is like some variables which have which might converge to something, some other random variable. And yes, well, what would be the most natural candidate? And thankfully, it works. Basically, we get some form where we would try to obtain normal random variable out of this. So basically, we just rewrite all things in terms of these variables nicely. And here where the unexpected trouble came into play. So, okay, once we rewrite it, so okay, here we have the ratio of variances, which is super easy to show that it converges to 1. And then we look at these expressions. So now, of course, we won't have almost sure convergence of these variables to something, but we'll have convergence in law. So we would like to use the Portmanteau theorem, which kind of allows us to pull the limit inside in some sense. Well, again, here is a singularity, so we need some way to know that this singularity won't cause any problem, so that we can use the Portmanteau theorems. Okay, and actually, so what we show is that xn and this x hat n, they converge in law to the same random variable, which is kind of easy to show. So what we show for dimension 4 and higher is that this variable is actually still normal. So even though, in the critical case, things are not so the decay of the Green's function is not exponential. It's kind of still enough. And then for dimension 3, it is some random variable. So basically we find an explicit expression for its characteristic function, which is nothing particularly nice. And it's so not nice that it's not clear that if this C would be 0, whether it still would be possible to conclude that this expectation is well defined. However, if we would know that this would converge to something positive, then we are good, because we know that in the mean it's 0 and it's non-trivial, so we would know that at least we have some positive probability for this interval. Yes, and this was a torture in dimension 3. So basically, there were already bounds existing. So one needs to understand, so this is, what is beta critical? Beta critical is GZD at the diagonal. And what we get here is basically the 0 average Green's function and 0, 0. And we need to understand really what's the margin between the two to be able to conclude something. Okay, so the known bound before was n to power 2 minus d, and here was log n correction to power 3d half. Actually, it works for dimensions strictly greater than 4. It's enough. For dimension 4, it already needed a better formula, so we would need like square root of log correction for this to work. But well, thankfully, actually, we found that the function actually differed by just n2 minus d, and actually what we proved is that the G0 average lambda n xy minus G zd xy, that this one is less or equal than distance x y to 2 minus d. So this is distance and forward. Well, some constant. So basically, there are no log corrections no extra log term corrections. And then for dimension 3, as I mentioned, so because kind of the law of x, it's explicit, but not sufficiently enough to conclude anything about well, how good it's, with what probability it's below 0. Let's say, so actually for dimension 3, we require that we are not only of order 2 minus d, but we are actually of some positive constant times that. And this was something that, well, we were finished with everything. This took us like another 3 months. But yes, and actually, maybe let me go a bit away from here. So understanding of this constant is actually related to some quantity in mathematical chemistry, which is called Madelung constant of electrostatic potential of some salts. And the thing is that this understanding, so basically what we were looking at, so how we derived this, we were looking at the zero average Green's function on the boundary. So, and we had to understand what kind of values it takes. So we didn't need like the precise values, we just needed the negativity of those values. And some of those values, basically the values at, well, kind of points which kind of come from the intersection of the torus with, if it's centered at 0, with the axis. Yeah, those are related to these Madelung constants, and one gets for them actually some explicit Fourier series representations, but they are not absolutely convergent. Actually, if one takes some quite natural truncations, they diverge. So yeah, it was painful, but we managed to do that. And actually, the interesting question which arises is to understand, like, for other dimensions, and also for dimension 3, what are actually the regions where this difference is still negative and where not. Okay, so now it's very easy to conclude. So basically have everything. So now we just need to use Portman-Drew theorem. Well, we use it for 2 functions, for upper and lower semi-continuous functions. So for the upper, we just cut out some epsilon piece, and for the lower, we just take whatever we had before. And then basically using that the, yes, for the lower, basically, okay, here we didn't use anything. We just know that Cn converges to C, Xn converges to X. And then, yeah, here we just cut extra some piece. So this would be even, this would be greater, even greater than this thing. And here we use the upper semi-continuity, where we have used, so we have showed that the density of these new variables were uniformly bounded. So basically, again, we can just integrate over some small piece of the function 1 over square root of x. And the remaining piece is nice enough to conclude the convergence. Yes, and the nice thing here is that, okay, if I mean for dimension 4 and higher, we show that C is 0, and X is a normal random variable. But for normal random variable, well, this is explicit, so one of course knows that there exists some positive number such that this is satisfied. And for dimension 3, we require that we know that this is strictly positive, and by some symmetric argument, we can conclude that actually, also in that case, there exists a function such that we can lower bound this expression.
Yeah. Also, x is always positive here.
No, x is a random variable. X is a normal for dimension 4 and higher. Yes. And for dimension 3, it's some random variable. And what is important here is C. C was like basically this difference of the GZD and the zero average thing. And for dimension 4, this converges to 0. And for dimension 3, this converges to positive random variable. Okay, so well, we have two expressions. Our RT to n was basically the ratio of the two, so we can conclude that it's less or equal than this expression. P here is a fixed number, and epsilon was kind of arbitrary, so we can send it to 0 and recover 1. And by just reversing the roles of denominator and numerator, we recover the other direction. Okay, well, I'm actually done. I don't know, maybe I have.
No, the time is oh,
okay.
Yeah.
Okay,
No.
sorry, then thank you.
No, but thank you very much. I am fixing the camera. Thank you very much, Aleksandra. So, are there any questions while I try to fix the camera? Yes. So.
Yeah.
So I have a question just about the ending. So in the case for d equals 3,
Mhm.
so how do you show that this expectation is positive? You know that C is positive?
This one is positive?
No,
Oh.
that's okay. The expectation, like so the last slide,
Oh, this one.
the one
Okay.
that's started from above,
So
like from below, I think.
so what we show is that, yeah. Okay, so we get okay, so we are looking at the expectation indicator function. Oh, well, I mean, so here we have some C minus X indicator function. C is greater than X.
Yeah.
Yeah. No, C minus epsilon. And this epsilon was at most C half. And C is positive here for dimension 3. C equals 3. Okay, well, so we have actually some characteristic function of X, which shows that it has some sort of continuous law. And also because expectation of X is 0, so it's a non-trivial random variable, so it's not just 0. So basically, it tells us that it takes positive probability and well. So basically, what we derive is that this story. So for some positive fixed constant sigma is strictly greater than 0. Well, and if you know this, I mean, this function, I mean, in worst case scenario, it can be infinite. Oh, well, you can't because this is strictly, so this is bounded by 1 over square root of epsilon. And basically this function is also non-negative. So basically, oh yeah, so the lowest value, so this X, so I mean, you get the integral from minus infinity to 0 plus this 0 piece. And well, I mean, okay, here you have some density. Well, I mean, if you know that this is positive, well, no, this is positive, and because this T half is kind of fixed, one changes. Yeah.
So you get
but it wasn't clear whether this is positive. Well, yes. So kind of we didn't quite know. Okay, not this. We didn't know. So for 0, yes, but we needed to subtract some epsilon there. This we didn't know. So we didn't know that if here we put some minus epsilon, we didn't know this. Yeah, that's why.
Question. So I have two questions.
Yeah.
So one is more concrete. Why is it different? What is the difference in between dimension 3 and 4, where you have this C which is not 0 or and 0?
Yes. The thing is that the variance of this gamma squared for dimension 3 is of order n4. For dimension 4 is an order n4 log n. And in dimension greater than 5, it's just n to the power nd. So the problem was here, the biggest eigenvalue. So if you consider the eigenvalue decomposition, so you rotate the diagonalize the matrix, the order of the eigenvalues of the bigger eigenvalue is n squared. So basically the n4 comes from the eigenvalues. The tail doesn't matter so much. While in the other cases, the tail is the one which is deciding. So this is also how we show that actually in dimension 4, and also in dimension 5 and higher. So for example, to show that in dimension 4 we converge to normal is a bit different than in 5 and higher. Again, because of here you just have D, and in the other case you have this. But this log correction is nice. It basically tells you that the tail is the deciding one.
You have another question, which is more ethereal.
Yeah.
So, I mean, I'm interested in the case where you get massive story.
Mm-hmm.
So the case where you have massive, like the 2-point correlation function of the sign decreases exponential.
Yeah.
Yes, but this is already on the limit. So there are two limits. You take a distance, and then what is missing to change the limit? That to say, like, there is an n big enough such that you already have.
You mean for the spin O or
for a spin O, for example.
For the spin O.
So
actually, okay, for the spin O, I think one can actually conclude it from a Kupyanian paper. So he has like one paper that he basically, which basically shows from which one can conclude, but we're not quite sure how rigorous it is. And the expressions that he's using there they don't correspond to anything. So what he's doing is, he's doing the same trick, like he adds the math term, but then he has this, he rewrites the Dirac matter in terms of I to some power, and then he gets basically a complex math, and then he looks at this basically as something like minus delta plus, I don't know, m squared plus I a or something, and derives some nice kind of expressions in terms of random walks for these guys. And then he shows that, well, if you plug everything back, you sort of would get so basically you would get that the correlations decay exponentially for the spin n for n sufficiently large.
Yeah, and in your story,
so the thing is that, well, we believe it's true.
Yes.
However,
but in your story, you would need somehow like a better convergence of the densities, or it would be much.
Our proof of spin n. So basically, what we show there, we fix lambda n. For fixed lambda, basically, to show that when n capital goes to infinity, we just use this kind of local thing. So because you're basically looking at. So you're looking at kind of things depending on lambda. So our proof won't work.
Okay.
So because here we're working here when lambda is fixed, this is a well-defined random variable which just depends on lambda coordinates. While if lambda goes to infinity, just this object won't be defined. So
thank you. So are there any other questions?
Yeah.
Yeah, my question is, I don't know if it makes sense, but if we can recover some geometrical property of the massive GFF given the convergence of these models to it, or
for geometric.
I'm thinking on maybe level sets or something.
Well, I think it's known much less about the spherical model than the GFF, so I probably wouldn't bet that it's the case. Because for a spherical model and things like this, the only quantities people know are some covariance structures or free energy.
Or maybe the inverse, or maybe we can understand.
Yeah, so it's more like if you know the GFF story, then you can say more about it.
Yeah, like the percolation type of question. It's not like this type of questions that Pierre-François has been studying. Like if you, like you know the threshold of the percolation on CD, can you somehow say that it happens for the spherical model, for example, like saying that they have the threshold start to coincide when?
But, yeah, this I don't know, but I can imagine that probably I think in the spherical model we have really good control on the things for the spin O, and I don't think from our result we can say anything, but for the spherical, I think it's much better because we have very tight and precise bounds for everything.
So any other questions on the theme? If not, we can, well, Aleksandra is around, so you can ask her, and let's thank her again. Tomarlo para buscar.
So this clock, they are wrong. They just run with the wrongs.
Yes.
It's never been on time.
No, I put it on time,
Yeah,
and I thought
once today.
but then it kind of started to move, and I was oriented, and I was like, how slow am I speaking?
No, but you finished like 50 minutes. It was great. So I was going to tell you, but I didn't want to. Because when I saw the clock, I said, oops. Yeah, they decide not to put good batteries on those clocks, so which is
None of the works of the university.
But it moved. I think.
I mean, no one needs a clock that doesn't move at the right speed, no?